Thank you, Erin. Now here, what I'm going to talk about is this part that I'm going to present now is relevant to our anomaly detection framework that we discussed previously, where we have two sensors. We get information coming from upstreams to predict downstream data and thereby detect anomalies. So before coming to the anomaly detection framework, now about the data wrangling process. This is a really important thing when it comes to any data science process. The data wrangling is very, very important because the data scientists normally spend 80% of their time cleaning data rather than creating insights. As a result, they only spend 20% of their time creating insights, the rest wrangling data. So this is a really important point. What we even when I started for the first time when I worked in 2019, also we had this problem. We got very messy data, and then we had to spend hours and hours to make it get it into a point where we can use that for the model building process. So now through this, in this demonstration, what I'm going to do is I'm going to explain what we did in our current case study. But at the end, I'm going to give some suggestions what we can do in the future to minimize this process, to make this process a user-friendly, more appropriate framework. Okay, so basically this document demonstrates variety of processes we use to transform our raw data into more readable, readily used formats. And here, this type of a documentation is very, very important because this reporting and documenting data cleansing process is very, very important for the reproducibility of our work. Okay, so I'm still talking about our previous studied area. So we got data from Priyanga Creek, National Ecological Observatory Network aquatic site located in USA. So here, the main motivation for us to use that one was because now in NEON, they usually have two sensors, sensor locations on rivers in the network where water quality is measured using in-situ sensors. So in our current site, the distance between the two locations is 200 meters. And then, so basically for the data, we did all our analysis using our software package. So basically we use, for the data wrangling process, we use a few main tools, popular tools. We use tidy tools. So basically the tidyverse gives you a collection of our packages designed for a data science projects. So basically it allows you to do the main things that you need to do that involves with data when it comes to data cleansing, the data import, tidying, manipulation, visualization, and programming. And another package that we use was library, the Lubridate package. And so with that, I'm coming to a few important things that we considered during our data cleansing process. So when we got out the data, when we observed that one thing that we noticed is, that when it comes to this NEON data, every fifth, they used a mechanism to prevent biofouling of water quality instruments. So what we notice is, in their data, every fifth observation in turbidity in both sites are anomalous as a result of the wiper on the optical turbidity sensor operating every 5 minutes. So during our data cleansing process, once we visualize it, so for example, here what you can see is the wiper anomalies in their original data set. Every 5 minutes, they have this operation, the prevent biofouling, preventing, in order to prevent biofouling on water quality data, they use this wiper operation. So that causes an anomaly. Now, when we have these type of things, that can have an impact to our proposed algorithms, the performance of our algorithms. So we need to remove these things before coming for the model building process. So as the first step, what we did was, now we identified that there's a pattern. So what we did was we removed those anomalies, those wiper anomalies from our data set before moving for the model building process. Basically, we use in this code, all these codes are freely available online. So in this code, what we did was we use a rolling window, and through that we identify in each, so basically a rolling window of size 5, and every window we try to identify the maximum value, and that we set to an NA, so that we can ignore the impact coming from that one. So we notice the same behavior in both upstream and downstream turbidity data. And then after that, once we identify those things, then we discard those wiper anomalies in turbidity series in both sites. Basically, we set those detected wiper anomalies to missing values. And then after that, we noticed that then another thing that we noticed is we got this data from Pringle Creek, and they have their own quality flags in they have their own quality control process. The neon data undergo an automated water quality assurance process as a part of the rigorous neon protocols, and are given a quality flag for each observation. Basically, that their data will undergo different tests. There are different types of quality tests carried out for neon data. These are some of the descriptions for these are some tests that they used. So the range test basically check whether every observation falls within a reasonable minimum and a maximum value for a given location and time of the year, and persistent test, and there are stochastic tests, spike tests. Likewise, they do lots of tests, and through that they try to come up with their own flags. They label these data. But one thing that we notice is now this is actually a visualization of their label data. Basically, for a majority of these points available in that data set, they have a specific label: step flags, null flags, range flags, spike flags. And here we can see there are lots of valid data as well, because due to these different notation symbols that I have used, we cannot actually read the valid data. But now we can see in this data set, they have labeled lots of data as they have given a specific flag for many different labels. Then what we notice is, and we observe the same thing in downstream data. Then what we understood is, now when it comes to anomaly detection problem, the detection techniques highly influenced by the way we define an anomaly. So identifying the proper definition of an anomaly is very, very important. And then the labels motivates from that definition. Basically, we label the data according to our definition. And now we have a different definition. In this work, our focus is only on technical outliers. And here in the current labeling process, we notice that they have a specific different labels for water quality events as well. So because our focus is somewhat different from, and since our focus is only on the technical outliers, we decided not to use this labeling process. We came up with our own labeling process. I'll come to that one in a minute. And another thing that we notice is, now here in our proposed algorithms, we use different types of conditionings. We use new information coming from past observations. We use new information coming from other variables of the same site. And also we use information coming from other upstream variables. So there, what we notice is the water quality variables measured by these in-situ sensors include turbidity, specific conductance, dissolved oxygen, and they have collected many different water quality variables from both upstream and downstream. And now for those measurements, for those variables, measurements are available at 1 minute frequency. But when we check the surface water level and the water temperature for both locations, we notice that measurements are available at 5 minute frequency. Now, since our model building process, we are using data from different, from other variables and data from other sites, we had to think about the timestamps inconsistency before moving to we had to address this timestamps inconsistency problem before moving to the modeling process. So here, in order to address this one, what we did was we aggregated data such that the timestamps match across 2 different data sets. So here, basically, we used this package Thicken. It allows us to create evenly spaced intervals to which observations can be aggregated. And then through that process, we were allowed to come up with a data set that match across 2 different data sets. So this code chunk does this matching, the aggregation part. And then after that, we combine everything together. So surface water level and water temperature from both sensors measures at available at 5-minute frequency. Because of this reason, we decided to go for 5-minute frequency data. We decided to use 5-minute frequency data for our final analysis. And this is so for some of our water quality variables, we had 1-minute data. Now, remember in our turbidity data sets, we had this wiper anomaly. So first we set all those wiper anomalies to missing values. And then what we did was we use a rolling window and we aggregate all the remaining points. So basically, once we remove one point, we have in our rolling window, we have four data points. We take the mean of that one when we try to aggregate our original data to 5-minute data. So that's how we aggregate all the data. Okay, so after completing that process, we came up with the 5-minute data. And then, as I mentioned earlier, the water quality flags available in NEON data are not necessarily technical anomalies. Therefore, we did not directly use any quality flags other than RAGE flags in this study. So since our definition of an anomaly is a little bit different, we came up with our own labeled data set focusing on technical anomalies in sense equipment. We got the support from water quality experts and it involved a manual labeling process. And during this labeling process, we used interactive graphics that allows us to operate to interact with graphical information present on the displays. So knowing all these tools and techniques is very, very important during this data wrangling process. And another thing is now we label this data. Our main purpose of labeling process is to evaluate the performance of our algorithms, but we don't expect the practitioners to do this process before applying our proposed algorithms. Okay, so basically that's how we prepared our original raw data. That's how we prepared our original data set, from the raw data. And at the visualizes, this is what we came up with. So basically now here we at the very beginning of the presentations, Kat gave you an introduction to different types of anomalies, the priority levels of those anomalies. Basically, we were focusing on those type of anomalies that we have identified in our previous work. And then we labeled both upstream and downstream data. And now this is the output of this data wrangling process, and we use this data set for our upcoming anomaly detection framework. Yes, so that's a brief summary to the data wrangling process that we used prior to the model building process. I'm happy to take any questions.